Okay, let's continue our review for the Unit 1 exam. So this is going to be a review of lesson number 2, which is on plate tectonics. So this corresponds to chapter 2 in your textbook. And the first topic that we need to discuss is how do we know, or what's our evidence for plate tectonics? And so you should know who Alfred Wegener is. So you should know that name, Alfred Wegener. And so he put forth the idea of continental drift, that the continents move around and they have bumped into each other and they have been pulled apart in the past. And so one of his lines of evidence is continental fit. So it just looks like South America and Africa fit together. But the problem with continental drift was that they couldn't figure out any force that would be strong enough to push solid rock around on the surface of the earth. So they just couldn't imagine that continents would be able to do that. So he was correct that the continents have moved around. He was incorrect in the idea that it was just the continents that moved. So later we're going to find out that it's the plates that move around, and a continent can be embedded in one of those plates. Okay, another line of evidence is going to be paleoclimates. And so there are certain continents that show evidence for glaciation. Places like, as you can see, like they're in Africa and in Australia, which today are very arid. How could they possibly have been covered in ice? And so if you take all of those continents, you can put them back together again to show where that ice was coming from. And so this was 260 to 280 million years ago. You don't need to know that date, but in the past, those continents were together and there was an ice age, which resulted in those parts of those continents being covered in ice, and then later they all broke apart. Okay, another line of evidence that shows that the plates have moved around is that some continents that today are frozen, like Antarctica, show they have fossil plants that are from the tropics. So that tells you that in the past, that continent was in a climate zone in the tropics, and then later it moved underneath the earth where it's all frozen. So we've found on different continents paleo evidence, fossil evidence for different kinds of climates. Okay, another thing is matching fossils, so that we've found the same fossils on continents that are separated today. Now, it could be that the exact same organism developed on both continents simultaneously, but that's very unlikely. It's more likely that you have one organism that evolves on a continent and then the continent breaks apart and it carries those organisms elsewhere. Okay, another thing is that we find matching sets of rocks on different continents. So maybe it's a certain kind of limestone, for example, and we find that same limestone in South America and in Africa, which is an indicator that at one time South America and Africa were connected together. Okay, so you should know about, if you're given a map of the ocean floor like this, you should be able to identify certain geological structures, okay? And we're going to go through those in just a moment. But you should be able to read a map of the ocean floor and identify how did those structures come into being. So for example, the thing that is going down the middle of the Atlantic Ocean, so that's going to be a mid-ocean ridge. But notice that there's another mid-ocean ridge to the west of South America, for example. You should also notice that there are trenches located in the western Pacific Ocean. So you should understand what is causing those trenches. Be able to locate those trenches on the exam. Locate major mountain belts for the exam, like for example the Rocky Mountains, the Appalachian Mountains, so the Himalayas. Okay, so you should be able to find all of those things on a map. So we at the end of this review, you will understand what causes fracture zones, what causes those trenches, and what causes chains of islands in the ocean. So what is some evidence for seafloor spreading? So first, what is seafloor spreading? So this is the idea that there are certain locations on Earth where the plates are being pulled apart and then it is forming new ocean floor. So lava, magma is coming up, it's filling in the crack where these plates are being pulled apart, and then that's forming new ocean floor. So this is going to be called seafloor spreading. So what's some evidence that the seafloor is spreading apart at these mid-ocean ridges? Okay, first of all, the thickness of the ocean sediment. So that the ocean sediment is the thickest near the continents where rivers are dumping sediment next to the continents. But so you got, let's say over here is Europe, and then over here is North America, and then you have the mid-ocean ridge, which is right in between. Well, that mid-ocean ridge is going to have the thinnest amount of sediment because that's where new ocean floor is being formed. And then the further away that you get from the mid-ocean ridge, the thicker the sediment gets. Another thing is the composition of the ocean crust versus the continental crust. So oceanic crust is made of basalt, whereas the continental crust is primarily composed of granite. So the ocean floor is composed of a different material than what the continents are composed of. Okay, heat distribution. So this shows that the mid-ocean ridges are very hot. That's because material from the asthenosphere, that magma, is coming up at one of those mid-ocean ridges. So you see that's that red area. Okay, then also notice earthquake distribution. So that at the mid-ocean ridges you tend to have earthquakes because the plates are being pulled apart and that ruptures rocks, and then when they rupture they vibrate, and then that produces earthquakes. Okay, you'll also notice that there are some earthquakes that are occurring around the ring of fire there, and we'll get to that in just a little bit. So you should know where are major earthquake belts located. It's where you have plate boundaries. So whether it's a continental plate boundary or an oceanic plate boundary, where plates come together, that's where you tend to have earthquakes. You notice there's not so much earthquake activity in the middle of the Pacific Ocean because it's in the middle of a plate. Okay, more about magnetism. So the magnetic field does not come out of the north geographic pole of the Earth. So that the Earth spins on its geographic north and south poles. The magnetic pole wanders. So currently it's off the coast of Siberia. But the location of where Earth's magnetic field comes out of the Earth, it moves over time. And the reason for this is because overall, the magnetic field is caused by motion inside the Earth of these magnetic materials going around in circles. Okay, but in addition to that, the material is also convecting. That means that it's moving up and down at the same time. So that tangles the magnetic field inside the Earth, and so that causes it to move around on the surface of the Earth. And so magnetic inclination is the angle that the Earth's magnetic field is going to make with respect to the surface of the Earth. So the magnetic field only is perpendicular to the surface of the Earth at the north and the south magnetic poles. At other places, it actually goes into the Earth at an angle, and we call that angle the magnetic inclination. The declination is the angle that the magnetic field makes with respect to the magnetic North Pole and where that's located at. Okay, so here's again a picture that shows that over time the location of the north and south magnetic poles changes. So we're going to call that polar wandering. Okay, you should also know something about magnetism and how rocks can be magnetized. So that the atoms that make up the minerals inside these rocks, the atoms are spinning, okay? And then it's the spinning motion of those electrons as they're in orbit around those atoms. That's what's really causing the magnetism of those atoms. But the problem is that those atoms can be randomly organized. So that so let's pretend that this is a particular mineral, okay? Inside of that mineral, there are going to be certain zones, and then these zones are going to be called domains. Okay, in this domain, the atoms might be oriented like this. So they are producing an overall magnetic field that is pointing in this direction. Okay, but then in this domain over here, those atoms in this domain are oriented that way. And then in here, maybe these are oriented like this. So the point is that when you average all of these individual magnetic fields, you get 0. So that's the reason why iron, for example, normally is not magnetic. So if you got a paper clip, you can't pick up another paper clip with a paper clip. Okay, it's because the iron in the domains are randomly oriented. However, if you were to take a paper clip and you put it in an external magnetic field and then you heat this piece of metal, then what will happen is these little domains will orient themselves with the external magnetic field. Then if you let it cool off, it locks them into position. And so now there is this particular mineral or rock is going to have a residual magnetic field. And that's exactly what happens as magma is coming up at these mid-ocean ridges. The magma is hot. It's composed of these iron minerals, which are randomly oriented. But they are in the presence of the Earth's magnetic field, and then as this material cools off and it hardens into a rock, then that rock has the remnants of that magnetic field locked into it. This is really important because we can use this remnant of the magnetic field of rocks to determine where was the magnetic North Pole at when those rocks formed. And then we can use that in turn to piece together where were the continents located at. Okay, then another thing about magnetism that's important is the magnetic field of the Earth reverses itself every 100,000 years or so. So the reason for this is that the magnetic field inside the Earth gets so tangled because it's going around and around and it's convecting at the same time that it snaps. And when the magnetic field snaps, it goes away for a few thousand years and then reforms in the opposite direction, so that north becomes south and south becomes north. Now, why is this important? Because that today, the stuff that's coming out of the mid-ocean ridge is hardening, those rocks are hardening, and have a magnetic field aligned with the current magnetic field of the Earth. But if you go 100 miles, 100 kilometers out, away from the mid-ocean ridge, you will find rocks that are oriented in the opposite direction because they formed hundreds of thousands of years ago when the magnetic field was pointing in the opposite direction. So what we find is stripes on the ocean floor of rocks. They're magnetic stripes that point north, and then the one next to them points south, and then the one points north on the other side of it. So all that we need to do is to match them up. So if we find this stripe on this side of the mid-ocean ridge, and then the stripe over here, and then we put them back together again, what that's going to do is it's going to take these continents over here and start to pull them together. And so by putting this all together, we can actually figure out where the continents were located at in the past. Okay, let's take a break. And when we come back, we will put it all together and talk about plate tectonics.